Hey guys, in this video we're going to learn how to analyze resistor networks. Now the ground rules for analyzing any circuit are Kirchhoff's laws. And this might be review for some of you, but if not, then these are super important. So Kirchhoff's first law says this, which probably contains a number of words that you might not be quite sure what he's talking about. So let's apply it to a particular circuit. So when it says the sum of the volts is 0 for any closed loop, well, okay, the word closed with regard to a loop means a loop that begins and ends at the same point. But what on earth is a loop anyway? Well, a loop is just a path around the circuit. And you can define a loop pretty much however you want as long as it begins and ends at the same point. So this is a loop. Here we go. I'm going to go around this way. Okay, all right. Or I could have done my loop a little bit differently. I could have done my loop like this. There we go. That's also a loop because I begin and end at the same point. The second really important point, though, about this, though, is it says that the sum of the volts is 0. And really, that's a fancy way of saying that however many volts the battery produces is how many volts the various resistors in the circuit are going to use. For a particular loop, all of the volts get used. So what I mean by that is this. If this resistor uses, let's say, 2 volts, then this resistor uses 7. Well, Mr. Erico, what about the... Oh, that one also uses 7 volts. Doesn't that... No, actually, that doesn't break any kind of rules, as I will help you to understand in a little bit. But for now, let's just get through the mechanics of it. Taking a walk around my circuit here. Here I am following this loop. That loop has 9 volts to distribute from the battery, and 2 volts get used there, and 7 volts get used there, and that adds up to 9. So we are happy because the sum of the volts around that loop was 0. Really, if you like, the battery uses or gives you 9, and these ones meaning give you -2 and 7 respectively. Also, for this loop that went around the perimeter, you can see also all 9 volts get used. Kirchhoff's second law says this. All right, so let's start with I, letter I, letter I. Oh, that's current. And a junction, what is a junction? Well, a junction is a place where 2 wires come together or split, or more than 2. It doesn't have to be just 2. You could have any number. So it's where wires come together or split. So those 2 points I just highlighted in red, those are junctions. So that means a couple of very important things here. One thing is that if there is a current flowing through this particular part of the wire, when it gets to that junction, it must split. Some of it will go this way, and some of it will go this way. And it's super important that you remember the following rule. Currents always go junction to junction. You should write that down. Currents go from junction to junction. So that means that I shouldn't have like one current that goes to this corner here and then it stops, and then I have a different current that no, come on. It's not at all like that. Current goes from junction to junction. Everything on this wire, if there were more than one thing on there, right, besides that one resistor, everything on that wire would have this current, whatever that is, flowing through it. Same thing goes for this middle branch here. Every part of that wire, including the resistor, has whatever the current through that wire is running through it. All right, so that brings me to the first current that I drew. I didn't actually draw that one right. That current also needs to go from junction to junction. So actually, I should have drawn it starting and ending at those 2 junctions. All right, so if I sort of recap it, what we have is this. The current in this branch splits at the junction into this current and this other current. All right, now one other really important thing that you need to be able to recognize for these circuits is where do you put what we'll call the total current? So to figure out where the total current goes is really easy. You just look for the battery. There it is. I found it. There's the battery. All right, now the battery is the source of all of the current in the circuit. And so whatever branch the battery is on, that's the one that you're going to label I total. If later on we see circuits with multiple batteries, there's no such thing as I total. But to begin with, we'll only have one battery at a time, and so there's I total. The other ones we can call whatever we want. We could call them I1 and I2, or we could call them like IA and I. It doesn't matter. You could call them Bob and Henry. It's fine. But the one we'll call I total is the one that has the battery on it. And so of the 3 resistors I drew here, only this one, receives all of the current that comes out of the battery, whereas the other 2 each only receive some portion of it. Now, we need to be able to use that law that Kirchhoff gave us, I in equals I out, to write what is called a junction equation. So to write a junction equation, you look at a junction, whatever, pick a point. And then you list out all of the things, all of the currents that are going into it, and you list out all the currents that are going out of it. So the only current that I see going into it is I total. The currents that I see going out of it are I1 and I2. And so if I in equals I out, I should write that equation up there. And that's a junction equation. Now, you may, or we will later see situations where there's like, say, a third branch or something like that, and then your junction equations will have extra terms in them because there are more currents. All right, but the basic premise of current in equals current out really ought to make good sense to you. Please remember, current is electrons flowing through the wire. If I total is, I don't know, let's say 3 amps or something, just to make up a number, and I1 is 1 amp, well then I2 would have to be the remaining 2 amps. Because if it were a different amount, where did the electrons go? That would be current disappearing. That means electrons being somehow destroyed, never reappearing. And that would just be not okay. All right, so current in equals current out. All right, now notice up to this point, I didn't label resistances on any of those. And that was because the resistances didn't matter. When I'm talking about Kirchhoff's loop and junction equations, in principle, I can talk about what the volts are doing and what the current is doing without needing any values for the individual resistances. Okay, so if I want to actually determine the values of each of these, then I need to put some numbers on the circuit. All right, so why don't we go ahead and do that? All right, now again, regardless of what numbers I put here, whether this was 16 or 6 ohms, right? This equation that I wrote up at the top is true. Regardless of what those individual values are, that equation is correct. Now, what will depend very much on the value of those resistances is what are going to be called loop equations. All right. Now, when we're writing the loop equation, there's actually only one formula that you need to know for a loop equation, and that is V equals IR. Oh, Mr. Errico, I already know that one. That one is Ohm's law. You're right, that is Ohm's law, and it's also the only one that you actually need. If you want to figure out how many volts a particular resistor is using, well, the answer is it's IR. So how many volts is the 6 ohm resistor using? Well, the current through it, I total. Okay, and if it's got 6 ohms of resistance, then I total, whatever that is, times 6 would be the volts that that particular resistor is using. Okay, the volts that the 12 ohm resistor is using would of course be I1 times 12. That's it. That's the only equation you got to know when you're trying to write what's called a loop equation, is IR. All right, but it has a particular format which is determined by the path of the loop that you are taking. All right, now remember, we defined what a loop was earlier. A loop is any path around your circuit which begins and ends at the same point. I usually like to start at the battery. That's what I like to do. And as I follow the loop, which I drew in the red dotted line there, that loop goes through, count them, 3 different circuit elements. It goes through the battery, the 6 ohm resistor, and the 12 ohm resistor. All right, now, in order to write my loop equation, I needed to have a couple of things. One would be the values of those resistances, maybe. Unless one's unknown, it could be called R, all right? And the other thing is the names of the currents that I drew in and made up. All right, I need those currents in order to be able to write that loop equation. All right, so following my circuit around, I have, okay, so first, if I'm going this way, I run through the 12-volt battery. So note up here, it says 12, right there, 12 volts. That's because the battery provides me with 12 volts. All right, if I continue on around, I go through the 6 ohm resistor. The volts used by it, we said moments ago, are 6 times I total, whatever I total is. All right, and I'm saying volts used, so that's where I've got this minus sign right there. Okay, all right, if I keep following it around, now I'm going to go through the 12 ohm resistor, which has a current of I1 going through it, and now I'm back where I started. There's no other circuit elements on that path, and so my loop is complete. So I write 12 for the battery, minus 6I total for the 6 ohm resistor, and then minus 12I1 for the 12 ohm resistor. Okay. Oh, Mr. Erico, hold on. What about the 6 ohm and I2? They're not in your equation. Did my path go through them? If the answer is no, then it really doesn't matter. If I didn't use a loop that includes those circuit elements, then I don't care about them, okay? It's kind of like if I did drive to the grocery store and then to the gas station, okay, then I only went to those 2 places, all right? And so those would be the only ones I actually include. Ta-da! All right, I shouldn't worry about the fact that I could also have driven to Target. Maybe that's what this other resistance, Target in my analogy. Okay, but I didn't go there, and so I don't need to worry about it in my, quote, loop equation. This is a convoluted analogy, but I hope you get the idea, which is your loop only includes some of the circuit elements. You couldn't even actually write an equation for a loop that would include all of them without making a figure 8, and those are just not allowed. You can't retrace the same path or part of the path twice, okay? Not okay. All right, but seriously, what about the 6 ohm resistor? Right now, what I've got is maybe enough information to get I total or I1 if I felt like solving for it. But what about I2? Surely I need to include that one somehow. You're right, and the way I include it is I write another loop equation. And there it is, another loop equation for following around the perimeter of the circuit. So probably a good thing for you to do, since you can pause me, unlike class, would be look at those 2 equations, okay? Look at the 2 loops that were drawn, right? Look at those red dotted lines. Those are your loops. And ponder where each of those came from, okay? Like, think about the picture that you have in front of you and the equation, right? Connect the dots before you move on, because everything hinges, like everything hinges on understanding how to write junction equations and loop equations. And if you can't do that, then you can't analyze a circuit. All right, so seriously, stop and ponder and make sure that those make 100% good sense to you. If they don't, then spend some more time thinking about it. All right, I think that's a good point to break to a second video in which we're going to go into a couple of examples that we will actually work out, as opposed to this one where we're just treating things theoretically, all right, being able to write the equations for it. So next up, we'll actually solve something.